The next talk is by Michael Shearer from North Carolina State University, and it's split between 45 minutes before the extensive lunch break and the second 45 minutes after.
Well, thanks, Uwe, and thanks to all the organizers for organizing a really very stimulating program. This first talk is going to be somewhat by way of light relief after Edgar's talk, which was very stimulating. So now you can all relax and look forward to lunch in 45 minutes or so. As Uwe suggested, there are two parts to the talk. And in the second part, I'll talk about an experiment which is represented here with this picture. So this will be explained in both terms of experiments and with some mathematics. But in the first part, I'm going to talk just about surfactants, just a few things that I found by trying to learn about surfactants myself, the basic sort of physics and chemistry of surfactants. And so I came across this little ad. Unfortunately, this special offer has expired. It was May 2013. But it suggests that if you really get interested in surfactants, you can go to your local surfactant store and try to bargain for 25% off. I should acknowledge a lot of collaborators here. Rachel Levy is in the audience. She's at Harvey Mudd College. She has many more undergraduates who are involved in experiments and theory and simulations. This is just a few of the students that I've met. Stephen Strickland is a graduate student at North Carolina State who did some experiments. This is actually his figure. And Karen Daniels is an experimental physicist, a colleague of mine also at North Carolina State. Ellen Swanson is also part of this project, mostly doing simulations. And she's at Center College, which is a very dynamic undergraduate institution in Kentucky. So here's an outline, actually, of both talks. And to start with, I'll mostly talk about what surfactants are to some limited extent and why we care, basically, the applications. And then the second part of the talk will be about experiments and theory. And so this is really the outline of the second talk. And the punchline is that the comparison to experiments is actually bad news. And we need to modify the models to explain what's going on in the experiments. The experiments are done very carefully in Karen Daniels' lab. And so the experimental results, I'm sure, are reliable. And then in conclusion, there'll be some idle speculation on what's wrong. Another thing that I found while surfing the web, surfing is appropriate for surfactants, was this sort of announcement of actually a couple of congresses, this 9th World Surfactant Congress and Business Convention. And here's the logo for the conference in Barcelona this year. And actually this represents surfactant molecules with a head and a tail. And I will talk about that in a little more detail. So this is kind of interesting that you could be in this World Surfactant Congress and feel very important if you're interested in surfactants. Okay, so let me talk about applications for several slides, and there are lots of pictures and a little bit of discussion. It'll sort of introduce you to the idea of what surfactants do. So mostly we're interested in, so surfactants are surface active agents. It's an abbreviation. They lower surface tension at interfaces. So not only liquid air, which is mostly what we'll talk about, but also liquid-liquid and liquid-solid interfaces. There are various biomedical applications. The area that got us interested some 10 years ago or so is surfactant replacement therapy for the lungs of premature babies, where their lungs have difficulty opening, and the injection of surfactant deep into the lungs allows them to take their first breath. And it was a revolutionary procedure to prevent deaths among very early premature babies. There's also a related treatment of lung disease to break up excessive mucus that accumulates in the lung, in particular as a treatment for cystic fibrosis, really just to relieve the coughing that is associated with clearing that excess mucus. So here's a picture of an alveolus, a rather complicated looking picture, but there's a fluid, the mucus is around the side here. I haven't given you a length scale here, which was a bit of a slip up, but in any case, there's a fluid surface, and the surfactant is on the surface of that fluid surface. So there's air here, fluid around the side, and then an elastic membrane, the cellular structure, and then these are all sorts of other biological structures that contribute to the operation of the alveoli. Surfactants also are in your eyes, and they're an important part of how your eye surface is wetted in the blink, and the surfactant is distributed with blinking. So there's one condition that's been studied actually by mathematicians quite extensively, the treatment of dry eye with surfactant, where you get holes in your lipid layer, the liquid layer that protects the eye. And here's a picture of, again, from my surfing of the web, of how that works. Now, you can't really read anything here, but it just shows you an eye. All right, here are a few more applications. This is a kind of an interesting one, that in remediation of contaminated soils, at the top you see a figure in a lab where there's a sample here which is being treated by flowing liquid from top to bottom, a little like Darcy's early work on porous media, and all sorts of chemical apparatus. And this is so it's a soil flushing process. And then this is a picture from a company, this Verutech company, their surfactant enhanced product recovery. And it shows that if you've got a contaminated soil, you have a monitoring well, we want to extract the contaminants, but you inject surfactants to loosen up the contaminants. And then there are more parts to the process, and in the end you get perfectly clean soil, which is remarkable. Another application is to nanotechnology, which I actually heard several talks in this program about the use of CTAB in manipulating gold particles and rods and so on, and mobilizing small particles. But it's also involved in manufacturing of thin coatings, especially associated with graphene. CTAB, by the way, is cetrimonium bromide. And finally, oil dispersant. If you have oil spills, for instance, the Gulf oil spill, then surfactants can be used to try and disperse the oil that's sitting on the surface of the ocean. Okay, so now we get into some slightly more sort of personal applications. So here is pharmaceuticals. So this is a graph that shows the influence of surfactants and ethanol on drug absorption, so the efficiency of drugs as they're absorbed in your digestive system. Here's the sort of a schematic of how detergents work, and here you see the structure again of the typical surfactant with what is a hydrophilic head and a hydrophobic tail. I'm going to show you some pictures of the chemical structure, but this is sort of the overall mechanism. And so here the hydrophobic tail is trying to stick to a solid surface. That might be the fabric of your clothes, or maybe your hair if you're using shampoo. And the hydrophilic head wants to be in the fluid. So here the hydrophobic bits are sticking to the dirt and lifting the dirt away, and then you wash it away when you rinse. So it's the same sort of process as cleaning the soil. And then finally I came across cosmetics. And this was kind of amusing. I have no idea what this picture is for, but the announcement is that Lubrizol is to meet surfactants demand with a new production facility. Okay. All right, and then here is another more serious application. I mean, they're all serious, I suppose, but I was sort of amused to see the cosmetics application. And it was all in pink. Yes, that's right. I should have pointed out that the graphic had so much pink that I had to put the title in pink as well, just to be consistent. So enhanced oil recovery. Surfactants and indeed polymers in general are used for two purposes. They lower viscosity, so the viscosity difference between, say, injected water and the very viscous oil, but they also lower surface tension, and that's valuable in secondary oil production. In this schematic, you've got an oil processing plant, a refining plant. There's oil that's being extracted from this well, and you're injecting all sorts of stuff down to force the oil out. And if you just inject water, then you tend to get fingering. And then when a water finger gets to this remote well, all you get out is water, and you've left all the oil behind. And so you try and minimize that fingering by putting in polymers or ASP, in this case, a surfactant. And the novelty of this company, Gulf Energy, LLC, is that they actually have bacteria as well. So this schematic from the same company shows these various processes going on. This is a sort of, if you like, the microstructure of the porous rock with some channels. There are microbes and the water path and so on. Okay, and there's text that you can read while I'm sort of chuntering on, and which has some content, but I won't linger on it. Again, they have an acronym for their process, which, of course, you have to have an acronym if you go into business. All right, so I said that surfactants lower surface tension, and here's that sort of hydrophobic tail, this piece over here, and the hydrophilic head, which is this entire head here. So it has a choline, which has nitrogen, and then various hydrocarbon molecules attached in a little structure like this. It has a phosphate, so with phosphorus in the center and oxygen around the side. And then this is actually a glycerol backbone, so that sort of attaches the two parts of the phosphatidylcholine, and this part is hydrophobic. So notice there are two tails here. Okay. So the other terminology that's used is that this is a fatty acid chain, and this is a polar head group, meaning that if you look carefully, there's a minus on this oxygen and a plus on this nitrogen, and that gives you a dipole electrostatically. So I'm not going to go into any details of surface chemistry, but just to mention that, this is a complicated subject scientifically. There's physics, physical chemistry, and chemistry, and all coupled into biological applications. Here again is a picture. This is now from Avanti Polar Lipids, which supplies our surfactant, and the lung surfactant is mostly this molecule DPPC, and in fact, lung surfactant has mostly lipids, but also has 10% proteins. And then this has to do with how ionic the molecules are. I showed you the picture with a plus sign and a minus sign, and that's Witter ionic. It has both plus signs and minus signs. So they make up about 75 to 80%. These are, again, the phosphatidylcholines, and the most prevalent one is DPPC. So here's the name, right? So I won't read you the name, but at least it only goes half a line. When we add in the fluorescent tag, MBDPC, the name, as I'll show you in the second talk, I don't think I have that name in this part, actually goes over a line and a half. So, to be a chemist, you have to be very good at pronouncing, multiple syllable words. I'm not a chemist, so I won't even attempt it. All right, so now you can see the molecular structure a little bit. Here's the hydrophobic tail, the two tails, and here's the hydrophilic head again. And this shows the chemical structure in symbols. All right, so we we want to have fluorescent molecules so that we can visualize them in experiments. And one way to do that is to have what's called a fluorescent tag. So in this MBDPC, it's the DPPC, but part of the amino acid chain has been replaced, actually in the 12th position, by a benzene ring with some more structure with hydrocarbons surrounding, and these are oxygen molecules. Anyway, so with an MBD benzene ring that's on one of the heads. And this paper I will refer to several times, actually. And they point out that the attachment of this chromophore, this little molecule here, onto this chain changes the properties of the surfactant monolayer. So what happens is that this piece will be sitting in the fluid, this part will be sticking up into the air, but they observed with by observing the surfactant surface potential with spectroscopic data, that this tail actually bends towards the fluid. And so what it means is that the fluorescently tagged DPPC takes up more area on the surface of the fluid than without the tag, and it changes the surface properties and therefore the properties of the molecule as a surfactant. So that's a bit of bad news, because the lung surfactant is DPPC, right? And if it's different from this fluorescently tagged dPPC, then results that we get for the fluorescent molecule may not have much to do with what's going on in the lung. Nonetheless, it's used extensively for experiments and for simulations. All right, so here are a couple of those remarks. And these aspects have really been studied in detail only very recently. So I thought I'd go back and start with a little bit on surface tension. And so here's the sort of classic experiment that you can do in your kitchen with a soap film. If you have a wire mesh or a wire shaped like this, and then a movable wire, maybe with rings on the side here, and you create a soap bubble, then if you measure the force that you exert on this movable wire, you can relate that to the surface area of the soap film. And so this is all governed by surface tension. So the one thing to point out here, here's a cross-section of the soap film. Here are the two wires at the top and the bottom, so it's somewhat thinner in the center. There are two surfaces, and the force is balanced by surface tension, which is really just a line tension. So there's a distance L here. The 2 is because there are two surfaces. There's the L, and gamma is the surface tension. It's measured in newtons per meter or variations on that. So it's like it's a stress. All right, and then so just to show you what a value the surface tension for water is 0.068 newtons per meter, just to orient you a little bit. Now, at the bottom here, I talk about alveoli, and this diagram really is just for just as suggestive of what's going on in the alveoli and why surfactants might be important. So let's consider a gas bubble, so with a fluid here in dark blue, and then air inside. And if the gas bubbles are just existing in air, then you have to balance forces across that membrane. So surface tension acts, I take a slice through the bubble. Surface tension acts on this line, and we know the formula. It's the length of the line times the surface tension. And then we have to balance that against a change in pressure. So there's pressure outside and pressure inside, and what's called the gauge pressure, or the jump in pressure, is given by 4 gamma over R from this balance. So the change in pressure times the surface area across this cross-section, pi R squared, has to balance 4 pi R gamma. Okay, so the jump in pressure goes like the surface tension over the radius, or more generally to do with the curvature of the free surface. So here, this is the radius of curvature. And so why is this significant for alveoli? Well, if we think of this soap bubble or water bubble as being an alveolus, then this is slightly misleading because the fluid layer actually sits on that elastic membrane. So this is really just an analogy. But what it says is that when you breathe out, the alveoli collapse to a small bubble, then the R is getting small, so the amount of pressure you need to generate to open the alveolus gets much larger. Right? It goes like 1 over R. But if at the same time you can lower the surface tension, then you can counteract that geometric effect. And what happens as the alveoli collapse is the concentration of the surfactant increases. In fact, it increases like the area. Right? So the surface tension, here I'm making a leap from surfactant concentration to surface tension, goes like the area. Right? So the surface tension is decreasing like R squared, and that counters quite dramatically this 1 over R tendency. So that's the way that surfactant works to facilitate breathing in and out. It's rather easy to breathe in, right? Your diaphragm generates a change in pressure, and you breathe in air. And you're opening up these tiny sacs, and the surfactant really helps in that process. So I thought this might be sort of and I'd give you some idea of how this surface tension force works with geometry, in particular curvature, to facilitate breathing. But the curvature will come in later, actually this afternoon, when I formulate the equations of motion. All right, so this is just a simple example which you can read, but I did want to point your attention to this introductory book, which is kind of nice. It gives you some of the physical background, the biological physics, with applications in health and life sciences. It's well worth getting. It's quite a big book, but it's really elementary, and this example actually is taken from that book. All right, so how does surfactants change surface tension? I'm not going to be at all quantitative here. I'm just going to tell you and then move on. So they basically, the molecular forces are modeled by some energy function. Okay, so that's a sort of basic principle. And the contributions to this energy function are from elasticity. Right? So this is like an elastic membrane, this interface. It can be stretched, it can bend, and it can be twisted. Right? So there are contributions to this energy function from all three effects. There are van der Waals forces, which are particle-to-particle forces, right? So short-range forces. And then there are electrostatic forces, which you might expect to come into play for these polar lipids, where you have pluses and minuses bias within the molecule. So physical chemistry, I mean, it's an enormous field which quantifies these effects in terms of the molecular structure, except that it's not a very precise science at this point. And a lot of molecular dynamics studies are done with a lot of assumptions to try and quantify how these relationships come into play, and then the experiments actually quantify the parameters. So there's a lot of detail which I'm certainly not an expert in, but just to give you an idea of some of the effects that come into how surfactants at the molecular level affect surface tension and how they might be incorporated into a theory. For these DPPC molecules, which are really quite complicated, have complicated structure, there's a lot going on. And so that's what I want to tell you a little bit about. What we're mostly interested in for modeling for the experiment that I'll tell you about this afternoon is how surface tension is related to the concentration of surfactant. And for that purpose, there's a comparatively simple experiment to do, a little bit like the wire in the soap film, where you measure the forces depending on the surface area occupied by the surfactant. So this picture, I'm afraid, is a little faint, but and I'll show you similar ones on the next few slides. So the picture comes from an apparatus called the Langmuir-Blodgett trough. Here's a picture of it. It looks as though it's some huge thing, if you imagine this as a computer terminal. But actually, here it is. It's the same thing. It's tiny. And this is in an enclosed space to protect from pollutants, because if you have any dust that lands on your fluid surface, that acts as a surfactant. So it's very carefully controlled. And what you get from this Langmuir trough, let's see if I have a picture of how it works, actually. Oh, yeah, in fact, here's the picture. Right, so you have two bars here. One is fixed, the sides are fixed, and you move the bar with a force, and so you're pressing actually on a layer of fluid, that's in blue, and there's surfactant between these two bars. So this is a side view, you're pushing on this barrier on the right, and compressing the surfactant molecules. Here you see the hydrophilic head and the hydrophobic tail. If you don't press very much, so you've got a large area here, then the surfactant molecules are sort of disorganized and widely spaced apart. As you press a bit more, they're still a bit disorganized, the tails especially, but they're closer together. And then finally, you get this compressed monolayer where all the heads line up. Okay, so the details of how that looks is a very sophisticated matter of using microscopy coupled with various techniques, which I won't tell you about in detail. I mentioned from time to time a little later on, maybe. And so here is a graph where you measure the area occupied by each molecule. So it's related, of course, to the total area that's occupied between these two barriers. But you calculate the area, this is in nanometers squared per molecule. Okay, so here we are in nanometers squared from 0.2 to 0.5, and then it jumps up to 10. Okay, so there's a little squiggle here which indicates that this axis actually goes out to the library. Okay, so it's a very long axis. We're seeing a little bit of the small scale sigma over this piece, and then there's another whole business that's going on. It's basically this picture, which goes out to 10 sigma, 10 nanometers squared. per molecule. All right, so this G part is this disordered phase. It's called a gaseous phase. L is for liquid, so this is like a liquid phase. It's a little bit more ordered, and there are jumps in this. Vertically is the pressure you're exerting, and there are various jumps in the slope here. And this is a horizontal piece where it's a mixture of liquid and gas phases. Then it's liquid for a while. The surface tension is a function of the area, or of the area per molecule. And then there's a different phase, another liquid phase, and then a solid phase. Now this is all done at one temperature. It's called an isotherm of the surfactant. Okay, so you control the temperature in this experiment as well. I was curious to see who Langmuir, who I knew a little bit about, and who Blodgett were, and so I sort of found nice photographs of each of them. And this is not exactly a biography of each of them, but one striking thing for me was that Catherine Blodgett was the first woman PhD in physics from the University of Cambridge in 1926. The University of Cambridge had been around a long time by that time. And she worked at General Electric, which is where Langmuir was. He hired her initially as an intern, and then said she needed to go and learn chemistry, which is how she got. She has a very complicated biography, actually, but essentially she went off and learned some chemistry and came back, worked at General Electric on surface chemistry, won various prizes, and is famous for various inventions. Langmuir also had a very distinguished career. He graduated in Göttingen and won the Nobel Prize in chemistry for his work in surface chemistry.
Excuse me.
Yes.
I just wanted to add something.
Yeah, please do.
Langmuir, it turns out, went to the high school where I live, near where I live.
Which is in Göttingen?
No, in Philadelphia.
In Philadelphia? Oh, right. Okay.
And he was recognized by the teachers as being quite gifted.
Yeah.
So they just gave him space up on the top floor of the building to muck around and do experiments. They didn't really make him take any classes.
I see.
Right, so they understood that he was a boy genius in addition.
Yeah. Okay. Great. Thank you. What's your name, by the way?
Randy Communion.
Okay. Good. Thanks. Right. So now here is a little bit more detail about what happens when you compress these surfactants. So here is the isotherm. This is actually drawn for a single-tailed surfactant, which I'll talk about from this paper by Kagner and Movold and Dutter. So this is a picture that looks a little like the picture we had from the Langmuir-Blodgett trough for DPBC. And we've got these various untilted condensed, tilted condensed. There's a phase coexistence, so it's like a liquid gas combined phase. There's a liquid expanded phase where it's sort of disordered in the tails. And then you jump out to 200, and that phase gives way to eventually the gaseous phase over here. Okay, so there's a big change in the area per molecule. Here, notice that the area per molecule is written in angstroms squared. Little exercise, look up the difference between angstroms and nanometers. All right, so the single-tailed surfactant, and they did a lot of experiments looking at the microstructure of these surfactants, and found a phase diagram where you look at various temperatures and the against surface pressure. So the isotherm here would be looking, somewhere over here at a constant temperature, increasing the surface pressure. And what you find, or what they found, is that there are different patterns for the organization of the molecules. So you can see sort of a hexagonal patterns in here. You can see rows with that are organized. But there's also the orientation of the molecules, and there's the orientation of the heads of the tails. So there are all sorts of order parameters. There are variables that determine which phase you're in. So they've identified all these subphases of liquid phase. And by the way, one thing that's interesting about these phase diagrams that you might not know is that there are two sorts of phase transitions indicated here. One is to do with a sort of radical change in the geometry of the packings. That's a first-order phase transition where you need to inject energy to achieve that. It's a little like injecting latent heat to go from ice to water. Okay? And so the first order phase transitions are these, the dashed lines. So here you're going from something that has a sort of row structure to something that where the molecules are all sort of sticking up in the air and have more of a hexagonal structure as indicated by the dashed lines. But over here, this rather ordered structure undergoes a second order phase transition, no change in energy involved, to something that's sort of more spread out, if you like, and is beginning to see that hexagonal structure. So there are all these subtle regions, subtle phases, changes in phase, depending on not only the packing but the orientation of the tail. And these there are various parameters. If you can see carefully, if you look carefully, you can see the various order parameters delineated. All right, and then there is a Landau theory of phase transitions where you have a surface energy, you expand about a specific phase transition with all the various parameters, just as a Taylor series. And then you have lots of coefficients. So, I mean, there are all of these etas and betas, all the Greek symbols are order parameters. Here is that same diagram which tells you what packings or orientations the various parameters are associated with. And this, and then you have to find these constants. So this is what I was meaning about finding the constants through experiment. So again, this is from Kagner et al., 1999. And so they used that theory to compare the phase diagram that you would get from the Landau theory with the experiments. I mean, that's remarkable agreement. And what's not quite clear to me is how much adjusting they had to do to get these boundaries to line up. But they interpolated from raw data to get the Landau free energy, and from there get this pattern with the various packings and orientation. So it's kind of a really sophisticated process which gives you very detailed information about how surfactants pack on a free surface. Okay. Now the Langmuir-Blodgett trough measures surface pressure, so I thought I'd just say something about the various variables that come up. So here's that. This now is from Sukhanova et al., the paper that I mentioned earlier. Here's the surface pressure against area per molecule. Again, this is in nanometers squared. And the surface pressure now is in millinewtons per meter. And this shows some of the contrast between DPPC, the lung surfactant, and the fluorescently tagged surfactant, the fluorescently tagged version of DPPC. So the DPPC, they were measuring some other things here as well. But the DPPC, so actually they're all listed here. The DPPC here has a sharp drop, and then it has something that's roughly horizontal here. So this is more like a liquid phase or compacted liquid phase, a mixed phase, a liquid phase, and then the surface pressure essentially is zero out here. NBDPC is much smoother, which is kind of interesting. There's no plateau. All right, so surface pressure is related to surface tension through sigma 0, which is the fluid surface tension with no surfactant, and sigma n is the surface tension with surfactant. Sigma n, actually, usually the m is used for maximum, but anyway, sigma m for surface tension with no surfactant, and the area molecule per molecule is measured in one of two different ways typically, and we'll call the surfactant concentration gamma, typically measured in micrograms per centimeter squared. Okay, I finish at 12, right? Yeah, okay, I've got it. All right. I think I've just got one or two more slides, actually. So here was something interesting that Sukhanova et al. Noticed, that at a small... So again, let me just orient you a little bit. So this is for NBDPC, the same surfactant that we've been using in our experiments. And, right. So here we're measuring the area per molecule. So this is in the picture on the left. It's at a fairly large area per molecule. So this is where the surfactant molecules are spread out. They've got plenty of room. And the distribution here, this is using epifluorescence micrographs. The distribution here is pretty uniform. And then they put some more pressure on, and they find in figure B, that's over here, so this is at an area below 0.82 nanometers squared per molecule, that you get interesting patterns arising. So these sort of flowery regions where you have much higher fluorescence, but there are also dark spots where perhaps there are holes, or perhaps there are some shielding in the optics. And then they claim or they observed that both of these patterns expand, both the white areas and the black dots expand as you increase the pressure. And here's another figure in this picture with Zhanger et al. From 2011, biomembranes. So this was really trying to understand the role of DPPC in membranes. They were interested in replacing this lung surfactant by manufactured surfactant, so Savanta, Curosurf, and others. And the black curve here is the DPPC. There's that plateau, so it's a slightly different. Here the surface area is centimeters squared, and this is the surface pressure in millinewtons per meter again. So here's that DPPC isotherm with the plateau and then going to a mixed phase. And they were finding that with these artificial surfactants, you get a plateau at a different level, and some of here's the DPPC with POP G in a mixture. So they're trying to mimic what's happening with DPPC, but also trying to figure out what's the role of all those other lipids and polymers in lung surfactant, because it's not only DPPC. So if you have a mixture like this, how does the isotherm differ? And so what they've done here is they've eliminated this plateau by just mixing 7:3 DPPC with POP G, whatever POP G is. So I thought that was kind of interesting too. All right, so now to make the transition to what we do, we did actually, Stephen did some Langmuir trough measurements, Langmuir Blodgett trough measurements with MBDPC. There are earlier experiments to try and quantify the dependence of surface tension sigma, we call it sigma here, on surfactant concentration. So the earlier experiments by Bull and others are these dots. They actually use something called a Wilhelmy pin to measure surface tension, and that's why there are just isolated data points. In the Langmuir trough, I mean, one of the advantages is that you can increase the pressure continuously. So you get more or less a continuous curve of concentration against surface tension. And then when the concentration gets very small, it's hard to make measurements, but you can see that this should come in roughly horizontally, as it does with the Wilhelmy pin experiments. Now, typically, the equation of state that relates gamma to sigma, so you write down sigma as a function of gamma and write down a formula for it to fit data. Typically what's done is this decreasing function. So surface tension decreases with increase in gamma, and then if you have a lot of surfactant, then you should go roughly flat. So you can make this like a 1 over gamma cubed to get it really flat for larger values of gamma. But actually, that misses the fact that you've got a flat piece up here and then a flat piece when gamma gets too large. So after gamma equals 0.2 or 0.3, the surfactant is really packed, and you start to see these a change in the packing of the surfactant, presumably associated with multiple layers of surfactant, which will not affect the surface tension, and that's why the graph goes horizontal out here at large values of gamma. Okay, so by way of discussion or summary, there are many applications of surfactants. There are various issues of importance to industry: adsorption at interfaces, which I haven't talked about, surface tension reduction, and then efficiency actually in dynamic situations. The pulmonary surfactant, the lung surfactant, is a very complicated biomedical system, and these sort of quasi-static experiments don't really capture what's going on in the alveoli, where there's a lot of dynamics. You're breathing in and out, and there's elasticity as well as changes in surface area. There are many recent attempts to clarify the roles of different constituents and how true surfactant, pulmonary surfactant, relates to the pure compounds. And I've just shown you really one slide that relates to that. Methods of study, we're mostly interested in something that captures really a gross property of the relationship between surfactant and surface tension, and that is this measuring pressure against area with the Langmuir-Blodgett trough. That's what's typically used for continuum modeling. So multiple phases can be probed with X-ray techniques, fluorescence microscopy, atomic force microscopy, and then there's a somewhat limited theory of surface energy, although there are experts on going from microstructure to surface energy in the audience. So one question is, does the surface tension depend on the liquid film thickness? Okay, so there may be interactions with a solid substrate if you've got a very thin film. Just something to think about. Okay, good, thank you. Yeah.
So in so you got your sort of hydrophobic part. So part of the molecules will be presumably lost from the surface when they sort of bind together.
Well, if they bind together on the surface, that's fine. That's going. But if they form multiple layers, where you have so you have the hydrophilic head sticking into the fluid, hydrophobic tail sticking up, then another layer which is sort of upside down. So that's typically what you'd see in a membrane, for example. But from the point of view of surface tension, that extra layer is going to have a much smaller effect on the surface tension, if any effect at all.
But if you're in the higher concentration regime,
Yeah.
so presumably more of this is going to happen. So
Right, yeah, exactly. Yeah. And the second part of the talk, I'll show you experiments in that regime. Yeah, thanks.
Actually, question about the relation actually between surfactants and potential actually sleep at the boundary. I think that everything that you talked about were more or less static, right?
Yes.
There's no dynamics involved.
There's no dynamics involved, that's right.
So that should probably have an effect, actually adding surfactants on the sleep at the boundary as well. If you have higher shear, usually actually get
Right, you get a Marangoni stress, which you can drive flow, and of course that's what we do in the experiments. Yeah, but the relationship between surface tension and surfactant concentration is typically from statics.
Is it okay to say that from a macroscopic perspective, I mean, you could look at it as that layer, if you have dynamics, a non-Newtonian type fluid, because
well, it's not. The surfactant molecules are not treated as a fluid. Right? They're just giving us a line tension or an area tension depending on surfactant concentration.
okay, so from
But in terms of how the molecules move around and interact with each other, yeah, I mean that's partly what the molecular dynamics community is about, except that they want to find the static configurations.
So from macroscopic perspective, I should just treat the addition of surfactants as changing surface tension at the interface.
That's the model that is used routinely in continuum modeling for dynamics. That's right. Yes, Andrew.
I mean, to add to that, it does depend slightly on the timescales. There are more sophisticated models that have surface diffusion and advection as well. So you can imagine it as a 2D surface. But
Yeah, we'll include surface diffusion, but yeah.
But the simplest is as Mike
Yeah.
said.
Final question.
Okay.
When you talked about this fluorescence stacking, you mentioned that the properties are then different. But what is the percentage of molecules that stack?
That
In
stack?
a typical experiment, we would just probably mix a tacked molecule and the standard one.
Stacked is what you're...
I mean, no, the fluorescence tagging.
Oh. No, actually, the molecules that are supplied by Avanti polar lipids are just the tagged.
Oh, then all of them.
Yeah, so you can.
Different surfactants, not the.
Right. So actually, so Rachel Eve is in the audience. We have talked about doing both, having untagged surfactant maybe in part of the regime and tagged surfactant in the other regime, and then you can see how one region moves into the other and different concentration. Yeah. Okay.
Okay, let's thank all speakers for joining.